So now that we've transformed our velocities into the center of mass frame, let's take a look at what the total momentum is in that frame using the expressions that we calculated on the previous slide. So we can write that the total momentum in the center of mass frame is equal to mass 1 times V1 initial in the center of mass frame plus mass 2 times V2 initial in the center of mass frame. And then we'll just expand out these expressions to arrive at some calculable total. So let's use our expressions for the transformation. So this is m1 times v1 initial in the lab frame minus the velocity of the center of mass plus m2 times v2 initial in the lab frame minus the velocity of the center of mass. And if you remember, this is the expression that we derived for the velocity in the center of mass frame in terms of the other variables. And so now let's expand out this set of parentheses. So this is equal to m1 v1 initial plus m2 v2 initial. These are both in the lab frame. And then I have minus m1 v center of mass minus m2 v center of mass. And so we can write this out as, let me collect this term here. So this is m1 v1 initial plus m2 v2 initial minus m1 plus m2 times the velocity of the center of mass. So let's copy this down here and expand the sum. So this gives me m1 v1 initial plus m2 v2 initial. And then I have minus this quantity m1 plus m2. And I'm going to recall our expression for the center of mass, the velocity of the center of mass, which is m1 v1 initial plus m2 v2 initial divided by the sum of the masses, m1 plus m2. So now if we look at this expression, this sum of masses here cancels this sum of masses here, but I have a minus sign. And both of these terms are opposite then to these terms here. So the total momentum in the center of mass frame is equal to 0. Now that basically has to be true because we're moving with the center of mass frame. And so the total momentum of the system, it basically has to be 0 by definition in that frame because the center of mass is at rest in that frame. And so any relative motion of the pieces of the system has to be such that the center of mass doesn't move at all because we're moving along with the center of mass. So it has to be true that this is equal to 0. It's nice to show explicitly that it's actually the case. OK, so now that we've demonstrated that, we go back to our idea of an elastic collision. So an elastic collision, we want the objects to bounce. And so in an elastic collision in this frame, the objects bounce. And so we would have that P1 final in our center of mass frame is equal to minus P1 initial in our center of mass frame, and P2 final in this frame is equal to minus P2 initial. So it looks like, in this frame, that the objects come in and they bounce and head back with the same momentum that they started with. So it's like they came in, hit a wall, and bounced off. So it's almost like the other object wasn't even there. So that's why we call this an elastic collision. In this frame, it looks like the objects come in, bounce off a wall, and go back out again. And so we can use this to derive a very useful relationship between the initial and final velocities. And so let's look and see how we can do that using these definitions now of what an elastic collision is. And so let's look at mass 1 and mass 2 separately. We can say that mass 2 we'll do mass 2 first, it doesn't matter. Mass 2 v2 final in the center of mass frame, let me use that expression that we did for transformation of velocities. So that's equal to mass 2 times v2 final in the lab frame minus the velocity of the center of mass. This has to be equal to minus mass 2 times the initial velocity in the center of mass frame, which is v2 initial minus vcm. And so if I look at this, I've got mass 2 times V2 final minus VCM is equal to minus mass 2 times V2 initial minus VCM. And so if I want to combine terms here, I can divide out the masses. The masses are going to cancel out. And I can write that V2 final minus V2 initial is equal to, if I bring this center of mass over here to the other side, I've got a minus sign here. This is all equal to twice the velocity of the center of mass. And I lost a minus sign. So I have this extra minus sign here, so this is actually a plus, just to make sure that all of that works. OK. So the sum of the two velocities is equal to twice the velocity of the center of mass. Clearly, I can write exactly the same thing for mass 1. I have mass 1 times V1 final, so I can, let's write it out just so we have a complete record. So mass 1 times V1 final in the center of mass frame is going to be equal to mass 1 times V1 final minus the velocity of the center of mass. And that final momentum has to equal minus the initial momentum. So I have minus m1 times v1 initial minus the velocity of the center of mass. OK, so when I remember the minus sign to move this over to the other side, remember that the masses are going to cancel out. And so I'm going to get, in this case, v1 final plus v1 initial. This is back in the lab frame, by the way, is equal to twice the velocity of the center of mass. So in fact, the sums of these two velocities, the velocity of object 2, the sums of the initial and final velocities of objects 2 and 1, are both equal to the same thing. So this gives us a very useful and interesting result, which is that velocity 1 initial plus velocity 1 final is equal to velocity 2 initial plus velocity 2 final. And this is purely a consequence of the fact that I have this elastic condition where these things bounce off in the center of mass frame. And so if we define an elastic collision like that, I get this relationship between the two initial and the two final velocities for each of the objects that's not derivable in any other way, unless we go and talk about energy considerations, which is sort of beyond the scope of what we're doing here. That's another way to arrive at this conclusion. And so the other interesting thing about this is that this is just a pure relationship with velocities. There are no masses in here. So this is true no matter what the masses of the colliding objects are, which is really interesting. And so we're going to use this to talk about elastic collisions because it's a very nice relationship between the initial and final speeds.